Hello, my name is Hyungwon Chai. I'm a PhD student in the Environmental Fusion Energy Technology Laboratory. Today, I will present a paper for the Clean Energy Technology class. The paper name is Comparative Evaluation of Performance and Electrochemistry of Microbial Fuel Cells with Different Anode Structures and Materials. This paper was published in 2017 in the International Journal of Hydrogen Energy. The order of presentation will proceed with introduction, materials and method, results and discussions, and conclusion. Introduction. Background. A microbial fuel cell is an environmental system that produces electrical energy from organic wastewater using electrochemical active biofilm on the anode electrode. An MFC application for wastewater treatment requires inexpensive materials, where electrode costs account for a significant portion. For this purpose, a simple, durable, and high-performance electrode structure is required. Good electrode materials have high stability and durability, large specific surface area, high electrical conductivity, and cost-effectiveness. So, various carbon-based materials have been used as anode materials, such as carbon paper, cloth, felt, or foam, graphite sheets, rods, and granules, and graphite fiber brushes. So far, various materials and anode structures have been applied to MFC. However, their comparative evaluation of performance and electrochemistry has not yet been investigated under the same condition. Purpose. In this experiment, a carbon cloth anode, an anode cathode assembly, and a carbon fiber brush anode with different orientations were tested under the same condition. The ultimate goal of this experiment was to identify the unique electrochemical characteristics of each anode and suggest strategies to improve MFC performance. Materials and methods. First, MFC construction. The single-chamber cube-shaped reactors were made with polycarbonate, having 28 milliliters cylindrical bed volume of 4 centimeters length and 3 centimeters diameter. The cathode electrode were made of carbon cloth, with a PTFE diffusion layer on the air-facing side, and a platinum catalyst layer on the solution side. 2 anode materials were used in this study. First one, carbon cloth was used as an anode. The second one, brush anodes were made from carbon fibers twisted between 2 titanium wires. Before inoculation, they were heat-treated at 450 degrees Celsius for 30 minutes in a digital muffle furnace. To compare the difference in performance by anode structures and materials, 4 anode types were tested. C is a general carbon cloth anode. EA is an electrode assembly type which made of a carbon cloth anode, a cathode, and a separator. VB is a brush anode located vertically to the cathode. HB is a brush anode located horizontally to the cathode. Inoculation and operation. The MFC was inoculated with 28 milliliters of domestic wastewater from Gwangju Wastewater Treatment Plant. Inoculation rate was 1:4, activated sludge with 5.6 milliliter, and primary sedimentation sludge with 22.4 milliliter. It was operated with 1000 ohms external resistance in a fed batch mode. When the voltage started to exceed 100 mV, the internal solution was replaced with the 50 mmol PBS medium. Medium was replaced when the voltage decreased to less than 10 mV. And then, 20 millimole acetate was added as a substrate. MFC was operated at 100 ohms external resistance, and voltage was measured by using a multimeter. Three, electrochemical tests. Measurement of polarization curves, electrochemical impedance spectroscopy analyses, and cyclic voltammetry were done with a potentiostat. For electrochemical measurement, an AGAGCL reference electrode was inserted in the medium and located very close to an anode to minimize anodic solution resistance. Polarization test. For polarization tests, the MFC was operated at 100 ohms external resistance for 3 hours after medium change. Then, it was set in an open circuit mode in a potentiostat for 2 hours, followed by an electrochemical experiment. MFC was connected to a potentiostat as below: a cathode to a working lead, an anode to a counter lead, a reference lead, and an AI plus lead. Reference electrode to an AI lead. Polarization curves were recorded through the linear sweep voltammetry technique by decreasing cell voltage from open circuit voltage to zero voltage with a scan rate of 1 mV per second. Power densities were calculated by using the following equation, where I is current, V is voltage, and A is cathode area. Internal resistances of anode and cathode were obtained from the slope of the linear part of polarization curves. Polarization curve measurements were performed in duplicates. Electrochemical impedance spectroscopy. EIS test for anode electrodes was carried out in a 3-electrode configuration. After the medium change, MFC was operated at 100 ohms external resistance for 3 hours. Then, the MFC was connected to a potentiostat as described below. The anode as the working electrode, and the cathode as the counter electrode, and a Gagel electrode as the reference electrode in potentiostat, when measured the anode. MFC was held in an open circuit mode for 5 minutes, and operated at an optimum potential in a potentiostatic mode for 20 minutes. Anode impedance was measured at an optimum potential for each anode, where maximum power is produced. 10 mV of the amplitude of the alternating voltage of the frequency range were used for anodic impedance measurement. Cyclic voltammetry. CV test for anode electrodes were carried out in a 3-electrode configuration. After medium change, the MFC was operated at 100 ohms external resistance for 3 hours as well. Then, the MFC was connected to a potentiostat as described EIS test, and then tests were performed. Anode potentials were scanned from 0.6 voltage to plus 0.1 voltage, with a scan rate of 1 mV per second to investigate the electrochemical activity of the anode biofilm. CV tests were performed in 3 cycles, and the final CV result was used for data analysis. Results and discussion. 1. Power density and polarization curves. Maximum power density in average was highest in the horizontally located carbon fiber brush anode, HB, with 1034 milliwatt per square meter, followed by VB, EA and C. Maximum current density in average was also highest in HB with 6319 milliampere per square meter, followed by VB, EA and C. However, optimal current density in average was highest in VB of 4137 milliampere per square meter, followed by HB, EA and C. The brush anode cells exhibited higher performance than the carbon cloth cells. The brush anodes showed 41 to 72% higher maximum power densities, 18 to 75% higher maximum current density, and 24 to 32% higher optimum current densities than the carbon cloth anodes. Polarization resistances for electrodes and a full cell were calculated from polarization curves. Anodic polarization were 62 ohms for C, 47 ohms for EA, 19 ohms for VB, and 22 ohms for HB. The brush anodes showed 25 to 43 ohms lower anode resistance than the carbon cloth anodes. Polarization resistances for a full cell were 167 ohms for C, 135 ohms for EA, 112 ohms for VB, and 132 ohms for HB, showing the brush anode cells had slightly smaller values. Cathode polarization resistance ranged from 88 to 109 ohms. Full cell polarization resistance was correlated with the anodic polarization resistance. Two, anodic impedance. For a more accurate analysis on anode resistance, EIS was performed at an optimum potential for each anode, where an MFC produced maximum power density. Anodic ohmic impedances in average were lowest in HB and VB, followed by EA and C. Anodic charge transfer impedance in average were also lowest in HB, followed by VB, EA and C. Anodic impedance in average were also lowest in HB, followed by VB, EA and C. The brush anodes had 1.6 to 21.2 ohms lower ohmic resistance, 7.7 to 10.6 ohms lower charge transfer resistance, and 9.3 to 31.8 ohms lower total anode resistance than those of the carbon cloth anodes. Anodic ohmic impedance in total anodic impedance was 47% in C, 9.2% in EA, 4.5% in VB, and 4.7% in HB for each condition. Anodic charge transfer impedance occupied 95.5% in VB, 95.3% in HB, 90.8% in EA, and 53% in C for each total impedance. 3. CV test. CV was measured to observe anode electrochemical reaction, with excluding cathode effects. For each type, anode CVs were measured in 3 cycles, and last cycle data was used. Comparing the amount of current produced by each anode configuration, HB produced the best maximum current with 4.04 mA, followed by VB with 3.36 mA, C with 3.18 mA, and EA with 2.65 mA. The brush anodes produced 6 to 52% higher current than the cloth anodes. Discussions. First, we compared carbon cloth and brush in terms of anode material. Because a brush anode has a large surface area, the brush anode can retain a large number of electrochemically active microorganisms on its surface. It can also have a large surface area for anodic electrochemical reaction, for electricity generation. EIS results also showed that the brush anodes had 34 to 43% lower charge transfer impedance than those of the carbon cloth anodes. And then, we also compared general carbon cloth anode and electrode assembly. In the EA, the anode performance could be detrimentally affected by oxygen permeation. However, since a separator was applied between the anode and the cathode in EA, oxygen diffusion could be minimized. Because the anode and the cathode are so closely located in EA and oxygen permeation was minimized by the separator, EA had lower anodic polarization resistance, lower anodic ohmic and charge transfer impedances, and produced higher power and current than those of C. 3. Anodic ohmic impedance. Anodic impedance showed that the carbon cloth anode had a high anodic ohmic impedance with 21.9 ohms, while the others had 0.7 to 2.3 ohms of anodic ohmic impedance. Anodic ohmic impedance is originated from contact resistance, anodic material resistance, and solution resistance. In terms of contact resistance, loose contact between a carbon cloth and a current collector could cause the high ohmic impedance. In the case of the electrode assembly, an anode, a separator, and a cathode are located together in a tiny space, where one carbon cloth was located in the carbon cloth anode cell. So a current collector and an carbon cloth anode can be connected tightly, reducing anodic ohmic impedance. In the brush anodes, the carbon fibers are tightly twisted between the two strands of the titanium wire by a mechanical device, resulting in a strong electrical connection between them. Therefore, we could have a low ohmic resistance of 0.7 ohms. In the carbon cloth anode MFCs, ohmic impedance of C with 21.9 ohms was so greater than that of EA 2.3 ohms. When an anode is farther from a cathode, ion transport pathway becomes longer, increasing ohmic resistance and decreasing power generation in an MFC. Conclusively, large solution resistance in an MFC could diminish anode performance due to slow ion transport between an anode and a cathode. Conclusions. The brush anode cells exhibited higher performance than the carbon cloth cells. Loose contact between a carbon cloth and a current collector could cause the high ohmic resistance. And large solution resistance in the cell could diminish anode performance due to slow ion transport. In order to improve MFC performance by modifying anode structures. 1. An anode should have large surface area. 2. Carbon material and a metal current collector must be tightly connected. 3. A brush anode should be located closer to a cathode. This concludes my presentation. Thank you for your attention.